Today we'll talk about the Klein-Gordon equation. We'll derive the equation, the Klein-Gordon equation. And it's an equation that describes the behavior of a relativistic free particle. Relativistic in the sense that the particle can have rather large speeds, in fact, speeds comparable to that of light. And a free particle in the sense that the particle is not subject to any forces. And so the Klein-Gordon equation is an equation of motion for a relativistic free particle. In fact, it was first formulated by Erwin Schrödinger in the 1920s in his development of quantum mechanics, and he discarded the Klein-Gordon equation, however, because it didn't yield the correct energy level spectrum for the hydrogen atom, and that's in part due to the fact that the Klein-Gordon equation doesn't incorporate the property of spin. And so we'll derive the expression, the equation, the Klein-Gordon equation, by promoting energy, the observable of energy, to an operator, a time derivative operator. So we'll quantize energy in that sense. So the name of the game is the Klein-Gordon equation. And from Einstein's special theory of relativity, for a relativistic free particle, the energy E can be expressed as the square root of the square of the momentum times the speed of light squared plus the rest mass of the particle squared times the speed of light raised to the fourth power. And we can have a positive or negative square root, but we'll keep the positive root. The negative one entails, when interpreted correctly, a positive energy for an antiparticle associated with the particle for which you're trying to find the energy. So for the electron, if you were trying to determine its energy, you would take the positive square root. The negative square root would give you the energy for its antiparticle partner, the positron, which has the same mass but opposes an electric charge in terms of sign. And momentum here appears as a square. So this means the dot product of the momentum with itself. And it's really the square of the magnitude of the momentum. Magnitude squared here. It's a scalar quantity, greater than or equal to 0. M is the rest mass, and that can be viewed in the following way. So the particle is moving in three-dimensional space. If you're sitting on top of that particle, then you're moving with it. The particle is not moving with respect to you. In fact, it's at rest with respect to you. And so the mass you would measure would be deemed the rest mass of the particle. Let's try and justify this equation a bit before we manipulate it to yield the Klein-Gordon equation. So one finds that if the momentum is 0, the particle is not moving at all, then we have E being the square root of the product m squared c to the fourth, but square rooting that gives us, as the energy taking the positive square root, mc squared. And we recognize that. That's Einstein's famous energy mass relation. So we can convert energy into mass and mass into energy. This mass, however, is rest mass. However, if we consider a massless particle with 0 mass, a particle with 0 mass, but having non-zero momentum moving in space, what would the energy reduce to? Well, let's see. So if we have m equals 0 for massless particle, then you see that the energy is the square root of the product of momentum squared with c squared. And that means the energy is the magnitude of the momentum multiplying the speed of light c. And we can do better. We can make this look like something more familiar to us. So de Broglie postulated that, correctly so I might add, objects have both a wave-like and particle-like character. And the wave-like feature is realized by the wavelength of the object, whereas the momentum-like aspect is extracted from the momentum of the particle, the momentum of the object. And that there's an intimate connection between the wave-like and particle-like characteristics, and that's known as de Broglie's relation. And it states that the momentum, the magnitude of it, is Planck's constant h over the wavelength lambda. So lambda is the wave-like characteristic of the object, momentum is a particle-like characteristic of the object, and they're inversely related. And lambda is also known as the de Broglie wave. So there's this inverse relationship between momentum and the wave. So then our energy for a massless particle moving through space is going to be h over lambda times c, or if you'd like, h times c over lambda. Now, if you consider a wave, like a water wave, traveling across the surface of a lake, let's say, you have these crests and troughs, these peaks and valleys. And if you'd like to measure the speed of the wave, the velocity of the wave, one way in which you could do it is to take a timer and have your eyes fixate at some point on the water surface and look at when a crest passes through and start your timer as that happens, as a crest passes, and stop the timer as the next crest over passes through the same point. And so that time that you've recorded is the period, the time for one wave cycle, the time for successive crests to pass through the same point. And the distance between those successive crests, the actual length between them, is the length of one wave cycle. That's called the wavelength, the distance between successive crests, the distance of one wave cycle. And if you take the wavelength, that distance, and divide by the period, that time, you get the speed of the wave, the velocity of the wave. So in other words, the speed of the wave is going to be the wavelength over the period. But the period is the inverse of the frequency. And so that means we can write the speed of the wave as the wavelength times the frequency. And so we see that the speed of the wave divided by the wavelength is the frequency. Now, why did we need this? Well, because we see something similar in the energy formulation here for a massless particle moving through space. With hc over lambda, c is the speed of a particular kind of wave, the electromagnetic wave. An electromagnetic wave, light is an electromagnetic wave. And so c is the speed of a light wave. And when we divide by the wavelength, we should obtain a frequency. In fact, we do, and that we call f. Right? So f is c over lambda. And E equals hf, you might have seen before, is the energy of a light photon, a particle of light. And that energy is directly proportional to the frequency. The frequency is larger, the energy is greater. And so if you have a beam of light with a collection of photons, then the energy of that beam would be an integer multiple of the fundamental unit of energy of a photon, a single photon, hf, and that integer is the number of photons in your beam. Now, it could be the case, however, that a particle may have mass, right, and is moving, is both having mass and moving through space, and then the correct formulation for the energy of that particle, so long as it's a free particle and can be taking on rather large speeds, is the one that we have up there, the square root of the sum of these two terms, one involving momentum and one involving mass. Now let's manipulate that expression. Okay. So recall, we had E being the square root of the square of the momentum times the speed of light squared times the rest mass squared times the speed of light raised to the fourth. Let's square both sides. So we'll have E squared equals, and on the right-hand side, the square root goes away. We have P squared C squared plus M squared C to the fourth. Now let's act from the right with a wave function that describes this particle, a single particle wave function. So that we have E squared phi. Phi is our wave function, call it psi if you'd like, is P squared C squared phi plus M squared C to the fourth acting on phi. So phi is our wave function. It's a function of space and time. So R is a position vector. It has an X, Y, and Z component. Those would just be X, Y, and Z, the X position, Y position, Z position. And if we take the modulus square here, that is, we take phi star phi, we find that's a probability density. That's in accordance with the Max Born's statistical interpretation of the wave function. So psi star psi, in this case phi star psi, the square of the modulus of the wave function is a probability per unit volume. Okay. Now, from quantum mechanics, we know that observables are promoted to operators. And in fact, the eigenvalues of those operators are the allowed measurable quantities. And such observables would be position, momentum, angular momentum. And we know that the linear momentum, P, this vector, is a vector operator. So you can put a caret on top to indicate as such that it's an operator, but I'll leave it out. You've seen this before, I hope, that the momentum operator is h bar over I, or minus I h bar, right, times the del operator, or the gradient operator. And that operator is a collection of spatial partial derivatives. So essentially, the momentum operator is a derivative operator in space, a spatial derivative operator. So del is I hat partial derivative with respect to x, plus j hat partial derivative with respect to y, plus k hat times a partial derivative with respect to z. Along the same vein, let's quantize the energy E. This observable, let's promote to an operator, but a time derivative operator. So we'll say it's equal to not h bar over I, but minus h bar over I, the partial derivative with respect to t. So it's a temporal derivative operator. And you might ask, why is that done? Well, you see, when I plug in for P, in the formulation here for the energy, right, I plug in for P squared, I'll find that I'll have a del squared term acting on phi, Laplacian. So it means I'll have a second order derivative in space acting on the wave function. And on the left side, when I plug in for E squared, I'll have a second order derivative in time acting on the wave function. So space and time will appear on equal footing in terms of the order of the derivatives they take on, second order. Right? In the non-relativistic setting, if you look at Schrodinger's equation, the time-dependent Schrodinger equation, you have I h bar d psi dt, or let me write d phi dt, equals h phi. So h is the Hamiltonian operator, and if we write out the Hamiltonian operator explicitly, it has a kinetic term and a potential term. We'd find minus h bar squared over 2m del squared phi plus some potential energy operator, which depends on position and possibly time, okay, acting on the wave function phi. And now you notice that on the right-hand side, you have a second order spatial derivative as expressed through the del squared operator. Right? So that's second order in space. But on the left-hand side, you have a first order derivative in time here. So time and space don't appear on equal footing. And this is problematic, especially if you want Lorentz invariance. If you want a quantity that remains unchanged under a Lorentz transformation. Okay, so going back, if I plug in for E and P, the expression I have here, I'll have, so for E squared, the minus sign will cancel for E. I'll get an h bar squared, and I squared on the bottom will give me a minus 1, so it's minus h bar squared. And then I'll have d2 phi dt squared, right? So the second order derivative of phi with respect to time, treating position as a constant. Remember, phi depends on time as well as space and time, space-time coordinates. For the first time on the right-hand side, let's put c squared out in front, and we have p squared acting on phi. So if we look at p, that'll give us an h bar squared. The I squared on the bottom will give us minus 1. And the del squared acting on phi will give us exactly that. So del squared phi, that's the Laplacian operator del squared. And that's d2 dx squared plus d2 dy squared and so on, plus d2 dz squared. And let's not forget the last piece, m squared c to the fourth times phi. Okay. And then to make it look more like what you would see in textbooks on relativistic quantum mechanics or quantum field theory, let me divide by c squared h bar squared on all sides. If I do that on the left, I'll have 1 over c squared d2 phi dt squared. For the first term on the right, the c squared will cancel, h squared will cancel, and the minus sign. Oh, I'm dividing by minus c squared h bar squared, the minus after. And so I'll have del squared phi. To the second term on the right, I have a minus sign. M squared, c to the fourth becomes c squared. And you have an h bar squared on the bottom. And this is the Klein-Gordon equation as I have it here, even in the preceding step, but let me write it in a more succinct way maybe. So let's put everything to one side. So I have 1 over c squared d2 phi dt squared minus del squared phi plus m squared c squared over h bar squared phi is equal to 0. So remember, phi is what we're seeking to find, right? So phi is what you're solving for here. This is a second order partial differential equation in both space and time. And what happens is if the mass term were 0, you have a wave equation, a three-dimensional wave equation, the solution to which is a function which has a fixed form of how position and time relate to each other. In fact, the solution can be taken to be plane waves, where you have something of the form e to the I, and then in parentheses, k dot r plus or minus omega t. K is a wave vector, omega is the angular frequency. And so this, with m not being equal to 0, is a modified wave equation. You can look at it down. So there's another way we could write this. So again, this is what we sought after, the Klein-Gordon equation. This describes the behavior of a relativistic free particle. And to write it in another way, let's see, 1 over c squared d2 dt squared. Let's factor out the derivative operators, minus del squared. Let's say that that acts on phi plus m squared c squared over h bar squared times phi is 0. So then what we have in parentheses, so the first term we can write as box, then acting on phi, plus m squared c squared over h bar squared phi is 0, where box is 1 over c squared. It's an operator, d2 dt squared minus del squared. It's a linear operator. Derivatives are linear operators. And then we can also say, if we factor out phi, box plus m squared c squared over h bar squared acting on phi is 0. That's another way of writing the Klein-Gordon equation. The box operator here is also known as the Derivation operator. Now, in quantum field theory, phi wouldn't be a wave function, but rather a field, a real scalar field. And we would typically set c and h bar equal to 1, so that the equation would look like box plus m squared all acting on our field would be equal to 0. And the field, quantum field theory, gets promoted to an operator. The field does. The observables like position and momentum are just labels upon which fields would depend. The fields themselves become operators, and that's known as second quantization. All right, I'll end here. Thanks for watching.